Hi guys, in Objective 118, students will be able to classify rational numbers. Okay. Some vocabulary that you have to know in order to classify rational numbers is what is rational. So a rational number is any number that can be written as a fraction with a numerator and denominator. And remember, the denominator cannot equal 0. Okay. Irrational is the exact opposite. An irrational number is any number that cannot be written as a fraction. Okay? Now, a natural number, think about when you are growing up and you're learning how to count. You usually start at the number 1. Sometimes you include 0, but usually when you ask a child, they're like, oh, it's 1, 2, 3, and they don't start at 0. So a natural number is any positive integer. We can write 1, 2, 3, all the way up to positive infinity. An integer is, and hopefully you know this, a whole number that can be positive or negative. I'm actually going to start off with a perfect square, the definition of a perfect square. So we're going to start off with 1, and if we do 1 times 1, we would get 1. So I'm going to draw this out. This is a perfect square. One side is 1, the other side is 1. We have 1 times 1, meaning that area, or that perfect square, is 1. The next number will be 2 times 2. That gives us 4. Again, drawing this out to give you a visual. This side is 2, this side is 2, then we have 4 in here. So our first perfect square is 1, our next perfect square is 4. Our next one, hopefully you're guessing this already, 3 times 3, we would get 9. And we would continue this process. An integer times itself gives you a perfect square. It multiplies to get a perfect square. I'll just do one more visual here. Okay. Now, the square root is the opposite. So if I take the square root, I'm going from example to definition. If I take the square root of 4, I'm asking you what value times itself gives you 4. So here, hopefully you're already thinking, oh, that would be 2 times 2. 2 times 2 equals 4. So the square root, or the number multiplied to itself to give us 4, is 2. 2 is the square root of 4. Okay. So the square root is the number or value that multiplies to itself to get a perfect square. Okay? So the first thing I'm going to say is we're dealing with rational or irrational numbers. These lie under a bigger umbrella of real numbers. We are not dealing with anything other than real numbers at this point. So here's my umbrella. Okay. Now, real numbers fall into two categories. So one, we have rational, and the other, we have irrational. All of these numbers lie on the number line. Any real number can be placed on a number line. Now, rational numbers are the majority of what we deal with. So again, the first thing, and we're going to use the definition, any number that can be written as a fraction, to prove if it's rational or not. So if we see 5/7, and you're thinking, I wonder if it's rational. Well, it's written as a fraction, so we know that it is rational. So that is the easiest way to check. Here are our fractions. Next, if we have a decimal, and again, an example would be 0.5, I can very easily rewrite this as a fraction because 0.5 or 5/10 can be rewritten as 5/10 or 1/2. So by that same proof, we've proved that a decimal that ends is also a fraction. Now, there are some decimals that will repeat. For example, 0.3, and this goes on forever and ever and ever. We should hopefully know that 0.3 repeating is the same thing as 1/3. So if you have a decimal that goes on forever, but it has a pattern, we can write that as a fraction. So let's make this key point here. This is kind of the challenge. That if a decimal goes on forever, but has a pattern, it is rational. Again, because it can be written as a fraction. If you're interested in knowing how to write repeating decimals as fractions, please join math team. So an irrational value, again, if we have fraction here and that makes it rational, then irrational means we cannot write these values as fractions. So really what we'll have to do is explore the decimal. Notice how here, if the decimal ends right away, 0.5, right? We can rewrite it as a fraction. Here, we will always have non-terminating decimals. So these decimals will go on forever and ever and ever. But if you notice here, we said that these rational decimals can go on forever, but they have a pattern. So 0.3 goes on forever, but that 3 is repeating over and over and over again. The difference is, if you have a non-terminating decimal and there is no pattern, then it's irrational. We wouldn't be able to write it as a fraction. Some of the most significant examples are, if you see pi, we know that this decimal goes on forever, and there is no pattern. Another one is taking the square root of a non-perfect square. So again, if we take the square root of 4, we get 2, which is a whole number, and we can simply write that as 2/1 or a fraction. So this would be the square root of a perfect square, making it rational. But 3, for example, is not a perfect square. And if you take the square root of 3, you're going to get a decimal that will repeat forever and ever and ever, but will have no pattern. So the square root of a non-perfect square. Oops. Really, the focus here is on the decimal, because it's either we can write it as a fraction or we cannot, and that depends on the decimal. Okay, moving to the next page. 2/7. This is written as a fraction. Here's the numerator, here's the denominator. So I know it is rational because it is written as a fraction. Okay. This next part, I see that this decimal is going on forever and ever, and this bar actually means that this pattern of 4, 2, 8, 5, 7, 1 is repeating on and on and on. So if we look here, 4, 2, 8, 5, 7, 1, 4, 2, 8, 5, 7, 1, we notice that there is a pattern. So although it goes on forever, since there's a pattern, it is rational. So there's a pattern in the decimal. So example 3 is interesting. We see that there is a numerator and a denominator, but notice that this value right here of pi, since it's in the numerator, if we decide pi, an irrational number, by 3, we are still going to have an irrational number. And we can actually test that out here. Oh, I'll change the batteries. So here we have pi. There's no pattern here. And if we divide it by 3, which is essentially what we're doing when we have a fraction, note that you have 1.0471975, and there's actually no pattern again. So even though we have a fraction, since there's an irrational component in our value, it is going to be irrational. But I did not just look and see pi and say, oh, it's irrational. I actually checked with a decimal. So pi divided by 3, no pattern in the decimal. You cannot just say because I know pi is irrational. That is not a good proof. Use your knowledge of what irrational and rational mean based on the definition. Alrighty, the square root of 32. Now, you should hopefully know there's no integer times itself giving us 32. So if we take the square root of 32, which I've done right here, I get a decimal that goes on forever, and there is no pattern. Also, square root of a non-perfect square, that's just a hint, but I'm still going to prove it. It's irrational because there's no pattern in this decimal that goes on forever. Okay, square root of 25, well, that is the same thing as 5. 5 can be rewritten as 5 over 1, which is a fraction, so it is rational. You should probably realize now that all integers are rational because they can be rewritten as fractions. We're going to stop here. We would like you to work on all of page 41 for sure, and also complete any homework that was assigned in class today. Come in with questions, and hopefully you enjoyed this video. Have a good day.